In the study of electricity and magnetism, we start with electricity. If I were to have some other point charge, Q2, some distance away from a point charge, Q1, I can find the electric force of Q1 on Q2 by knowing that the electric force is proportional to the charge Q1, it is proportional to the charge Q2, it is inversely proportional to the distance between them squared, it is on a line from point 1 to point 2. That unit vector just lets me know that's the direction. And because we will typically use coulombs for charge, often meters to represent distance, because the universe does not know what units we're using, then we will need some constant in front to account for that. And that constant in the case of electricity is 1 over 4 pi times epsilon, the permittivity of space. Epsilon naught, the permittivity of free space, is used when we're looking at the vacuum, or air. Air is pretty gosh darn close. If we were to, at some point, work with, try to find an electric force inside, say, lime jello, then we'd have to look up the permittivity of lime jello and go from there. Now, that's for a specific point Q2 located someplace else. That was not enough for us. If I'm looking at some charge, let's say that instead of having some known charge Q2 here, let's say that it represents some point P. And at that point P, well, this other charged particle the existence of one charged particle will result in an electric field. If you have charge, that charge will establish an electric field, the effect of that charge in space. And we can define the electric field at point P as being equal to, for a point charge, 1 over 4 pi epsilon naught times Q1 over r squared, and then radially outward from point 1 through point P. That's the electric field. Now, if that point charge is at rest, it's not going to generate a magnetic field. But if it's in motion with a certain velocity v, and some position located like so, given by r, then the magnetic field that's generated at point P, well, that depends on the charge Q. It also depends upon its speed v. Now, it also is going to depend on the sine of the angle between v and r, defined like so. In the same way as the electric field, the magnetic field falls off as 1 over r squared. And in the same case as the magnetic field, there are no magic units that the universe knows we're working in, so we need to account for that. And when we're dealing in empty space, that constant is given by mu, the permeability of, well, in this case, free space, which is very close to the permeability of air, which is very close to, well, which is defined as exactly 4 pi times 10 to the negative 7th meters per amps, actually Tesla meters per amps, where 1 Tesla is the unit of the unit of the magnetic field. Now, this actually allows us to find the magnitude of the magnetic field. The direction we'll have to define using the right-hand rule. Well, we define that using the right-hand rule by looking at this more closely and saying, okay, I can write the Biot-Savart law to find the magnetic field given by a moving point charge in this way if I know that to find the magnetic field, that's equal to mu naught over 4 pi times the charge times the vector, the velocity vector, crossed onto the magnitude of r. Just that part that tells us the direction of r. And then divide that by the distance between them squared. The reason why I wrote it in this form, which is mathematically a bit more complex, is so that you can look at this and see, okay, that's how to find out the direction. If I have V cross R, well, in any of the ways for finding the right-hand rule, the magnetic field is going to be out of the board for a positive charge Q. For a negative charge Q, that will take the resultant and flip it by 180 degrees to go in the other direction.